All right, vectors. So the key thing about a vector is that it has a size and a direction. Those two things together make something a vector. So velocity says that you're going 3 kilometers per hour north. That makes it have a direction and an amount, a magnitude. A scalar, as opposed to a vector, just has a magnitude, has no direction. So a distance.
Where are you getting this? I just looks different.
Oh, it is different. Okay.
This is why we shouldn't do this unit.
We should just skip the unit, eh? There we go. We can still highlight stuff. Here's your scalar. That just has magnitude. There's your distance and speed. And here's your vector, which has a size and a direction. Happy highlighting. So what I want you to do is you've got all of these examples. And I want you to put beside them whether you think they're a vector, a scalar, or neither. All right, how did you do? Scalar, scalar. Those ones have no direction. You've got a speed there in B, but there's no direction. Outside temperature is just a measurement. If you have just a direction, like the wind is blowing from the south, that's neither. If we gave a speed to that wind, then it would be a vector. But in that case, it's just neither. So in E, that is a vector because you have a force and it has a measurement, and then you also know which direction it's going because it's going upwards. Finally, on the next page, so the last one's a vector because you know it's going down. So each of those ones has a direction and a size. So we show a vector by drawing an arrow over top of it. Okay? Some textbooks you'll see that they'll show a vector by making it a bold one, but what we're going to do in this course is we're always going to put an arrow over top of something to show that it's a vector. Now, a vector, let's say we knew the coordinates of this point. Looks like we've gone over 5, up 4. Then we often write a vector as a column. And so we would write that 5, 4, we'd put the x on the top and the y underneath. And we'd write 5, 4 as a vector. So these ones are all bolded here, but what we can do is we can put arrows over top of them. To show that. What we call anything that starts from the origin and goes to any point, we call that a position vector. So when you have the coordinates and you start from 0, 0 and you go to a point, so 5, 4, this 5, 4 would be called a position vector because it starts from 0, 0 and it goes 5 to the right and 4 up. So here we have a vector v. It goes to the point 6, 3. You could write that as a column vector with the 6 on top and the 3 underneath. So again, here it says that it can be written as bold, but for the most part, we will write things, because it's very hard to write things in bold with just your pen. You could spend a lot of time, I guess, going back and forth, but we'll just write a little arrow over top of it to show that it's a vector. So it's going to be one of those things on quizzes and tests. You know, on integration, you had the plus C thing that you had to remember to do, or you got a -1 deduction on a quiz or a test. The vector arrow on top for every single vector will be your thing to remember in this unit. You'll also see some places, instead of the arrow over top, underline them, but I think it's nice. We'll stick to doing the arrow over top. So how long a vector is how we can show its magnitude. Now here you have the absolute value signs. That means what is the distance of something, and you can find the magnitude by just using a squared plus b squared equals c squared. So if you think about the point 6, 3, 1, 2, 3, 4, 5, 6. Well, to get to 6, 3, you have to go over 6, up 3. That will make a right-angled triangle every single time. So if you want to find the length of this vector right there, all you have to do is a squared plus b squared equals c squared. So c is equal to the square root of 45. You could write it like that. Or if you wanted to simplify it to 3 root 5, you could do that as well. So some properties of vectors. Two vectors are equal if they have the same length and they go in the same direction. So this is a little bit different than some equal things that we've had before, because if you're on, it doesn't matter where they start and where they end, as long as they are the same length and go in the same direction. So for example, if this one went up 2 and over 3, even if you have another place where it started at a different place and went up 2 over 3, those vectors would be the same, because they would go in the same direction and have the same length. If you multiply a vector by a scalar, so if you would take this vector v and double it or triple it, you're going to get another vector that's still going in the same direction. It's just going to be longer or shorter than what you had to begin with. And if you multiply it by a negative, the negative just flips the direction around. So negative 3v is still parallel to the vector v, but now it's going in the opposite direction. And here's another definition. The unit vector is a vector that has a length of 1. So with that idea of unit vectors, we get some standard unit vectors, and we use I and j for our standard unit vectors. The vector I is just going 1 to the right, or 1 in the x direction. And the vector j is just going 1 up, or 1 in the y direction. So our column vectors, 6, 3, can be written with our unit vectors, 6i plus 3j. Because what this means, 6 and then I is like this, and j is like that. And you can sort of think of them almost like matrices. How would I put these together? How would I multiply these and add these as matrices? Well, this one would be 6, 0, and this one would be 0, 3. And if I added corresponding elements, I would get that same column vector 6, 3. So 6i plus 3j is another way of writing the column vector 6, 3. So if we were looking at each of these vectors, and I'm sorry, on your paper the photocopy got all, the arrows got shifted a little bit, but this is what it was supposed to look like. So for A, can you see that you go 3 to the right and then 2 up? So you could write this vector A is equal to 3i plus 2j. Can you see where you're going to be tempted not to write the arrowheads over top of things? Vector B down here, well, now we're going 1 backwards. So that's going to be negative I. And we're still going 3 up, so that'll be plus 3j. I'll get you to do C and D, and then I'll write the answers up in a second. All right, vector C is 2i minus 4j, and vector D is equal to minus 3i minus 1, 2, 3, 4, 5j. So there's an arrowhead on our vectors, so that means when we're figuring out how we're going to count, this is where we're starting. We're going 3 in this direction and then 5 down. So that's why both of those are negative. Yeah, I can go back. Now, what makes vectors so powerful and what we're going to see about this is that the rules and the math that we learn using vectors is stuff that we could do in 2 dimensions using our equations of lines and stuff that we've used in the past. But we can use vectors quite easily into 3 dimensions as well. And so now we can solve all sorts of problems in 3-dimensional spaces. So we're going to add a new vector, a vector k. I'm going to add the arrowheads over here if you like. And then that adds our z-axis. So now, it's a little bit hard to draw 3-dimensional stuff on paper, but this is what you got to kind of imagine. Imagine, here I'll take out a piece of scrap paper, and you draw your normal x and y axes on your scrap paper. Right, there's our normal 2-dimensional x and y axes. Now, if you put that down on a table and added a z-axis that went straight up and down, when you draw that, you kind of have to imagine I'm taking my piece of paper and I'm laying it down, and on the table when it's laying down, there's my x-axis, there's my y-axis. This is still 90 degrees, but it's in 3 dimensions now because you've laid it down. And now you add straight up and down a z-axis. So if we wanted to label -9 for the x, 3 for the y, and 4 for the z, we would go to our x, y, and we would find the point -9, 3. So there, you could see it, that's where it would be on our x-coordinate, right? Then from that point, you think of your z-axis going up, you'd have to count 1, 2, 3, 4 up from there. Now, as far as drawing that goes, and maybe I should have, well, on here, what we've done is we've sort of imagined this is the point where you've gone -9 over and 3 up on the y. So if 3 is this distance along here, you go on the same slope 3 that way there. Then however much it is to go up 4, you go up that same distance there. And then you have your vector that starts at your origin and goes to -9, 3, 4. Can you see it? Now, if you want to figure out how long that red vector is, what you could do is, because you know this length is 9, this length here is 3, and this length is 4, using the math that we have up till now, can you see that that diagonal right there is just in 2 dimensions that length right there on our paper? And you could use a squared plus b squared equals c squared to find that dotted green line. And then once you got that dotted green line right there, there's another right angle triangle here with the green and the blue lines, and then you could find the red line. What I'm going to show you, I'm going to redraw this red line there. I'm going to redraw this blue line here and this green line here. And I'm also going to draw these black lines that we had to begin with. Okay? I'm going to call this my x, this my y, and this blue one my z. I want to find out how long that red line is. Do you agree that your green line, which I'm going to call G because it's green, your green line is going to equal x squared plus y squared equals g squared. So if you square root both sides, you'll get x squared plus y squared. Can you see that? And can you see that your red line, which I'm going to call R, is just going to be the square root of g squared plus z squared? Does that make sense? Now, if g is equal to the square root of x squared plus y squared, and I square it, then your g is just going to become x squared plus y squared. And then you still have plus z squared. So what's really cool is you've got a squared plus b squared equals c squared in 2 dimensions, and now in 3 dimensions, you've got a squared plus b squared plus c squared equals d squared, or x squared plus y squared plus z squared equals d squared. So it's kind of the exact same idea, and if you went to 4 dimensions, it would do that again, although it's very hard to draw 4-dimensional stuff. We're not going to make our brains explode quite yet. So if we wanted to find, I think this is going to turn out really cool. If we wanted to find the length of vector v, so we can show that by using the magnitude of vector v is going to equal the square root of -9 squared plus 3 squared plus 4 squared. 81 plus 9 plus 16. Or the square root of 106. So I'm going to get you to find the length of all three of those. First one, did you recognize the first one as a 3, 4, 5 triangle? Or did you still do the a squared plus b squared equals c squared? The second one, you get the square root of 75. You could reduce this to 5 square root of 3 if you wanted to. And now, if you really enjoyed Pythagorean triples, like 3, 4, 5, or 5, 12, 13, ones that end up with nice numbers, now you have them in 3 dimensions too. Here is a nice triple, the 6, 3, 2 triangle-ish, because the length of that is perfectly 7. So Pythagorean triples are like 3, 4, 5 right-angled triangles that work out perfectly so that all the sides are integers. But now we've got things in 3 dimensions, like the 6, 3, 2. If we drew this, oh, let's see if I can draw this nicely. 6, 3, and then up 2. This vector right there has a perfect length of 7, and all of its components are nice numbers as well. I don't know. I like those kind of things. So there you go. You can set it up and then solve for a. Square both sides to get rid of the square root. And solving for a gives you the square root of 42. But when you square root both sides, you have to remember plus or minus. Well, because if I have x squared is equal to 9, 3 squared is equal to 9, so x could equal 3. Negative 3 times negative 3 is equal to 9, so x could also equal negative 3. Same thing with x to the 4th. Anytime it's an even power there, when you 4th root it or square root it or 6th root it or 8th root it, you have a possibility of positive or negative. No. You can if you want to. Can't remember if the answer key is rational or not. Probably is. That would make sense. Okay, bad jokes for the day. All right, how did you do? I was recording the whole time while making bad jokes. Oh well. There we go. So you find the length of A is the square root of 29, and you could write your unit vector that way. Your length of B is the square root of 61. We want to find a vector of magnitude of the square root of 7 in the same direction as that vector. So we have this vector which goes 5 in the x direction, 3 in the y direction, and then 2 up. So maybe it looks something like this. I'm going to call that vector v. What you could do, however long vector v is, we could divide by that length, and then you're going to get the unit vector v. Does that make sense? And then if you want to find another vector that's in the same direction that has a length of root 7, does it make sense that we could now take our unit vector, which has a length of 1, and multiply it by root 7? So this is the idea. If we can first find our unit vector, then we could find another vector by multiplying by root 7, and then it will be in the same direction as the vector that we started with. So first of all, what is the length of our vector v? Well, it's going to be the square root of 5 squared plus negative 3 squared plus 2 squared. 25 plus 9 is 34, plus 4 is the square root of 38. So our unit vector will be 1 over the square root of 38. I'll write it as a column vector now. 5, negative 3, 2. And finally, if we multiply this by root 7, so we're going to get the square root of 7 over the square root of 38 of 5, negative 3, 2. It is a vector in the same direction with a length of the square root of 7. So again, the idea was if we first find our unit vector, then we could find vectors in any length possible just by multiplying our unit vector, which has a length of 1. Right? This one has a length of 1. You could find a vector in that same direction of any length by just multiplying.